Hi, buddy. This is Mr. Folly. Hey, that's me. And welcome to part 2 of the worksheet. Okay, so what is the final temperature of the metal? Justify your reasoning. So 50-gram sample of a metal is heated to 75 and placed into 50 grams of water at 25. The temperature of the water rose to reach the final temperature of 26.4. What is the final temperature of the metal? 26.4. Justify your reasoning. It cooled until it equaled the water. Which substance had the largest change in temperature, the metal or the water? Metal, right? 75 to 26.4 is about 50, and this was about 1.4. Which substance had the largest change in average energy, the metal or the water? Justify your answer. They are equal. The energy includes mass and C. Water has a high C. Explain at particle level how the temperature of the water increases after the addition of the metal. You're going to explain the role of kinetic energy. So kinetic energy is the energy of motion. So high kinetic energy, metal hits and gives energy to lower energy water. H2O goes up in energy, metal goes down. All right. Student claims thermal equilibriums reach at time T. That's where the temperature stops changing. What is thermal equilibrium? Temperature of all touching things are equal. Student correct about time T. Justify by referring to the graph. Yes, temperature is equal and not changing. Particles are still touching and they're still bouncing into each other, but the transfer of energy is the same. What can be said about the average kinetic energy of the metal and the water at time T? They're equal. Sample of iron, equal sign there, at 25 is placed into a sample of water at 75. Before the iron is placed in the water, how does the average kinetic energy of the iron compare to the average kinetic energy of the water? Fe is less, or has less. Okay, so it's being a big pain right now. All right, what happens to the temperature of the iron once it's placed in the water? So in this case, again, we have cold Fe. What happens to the temperature of the iron once it's placed in the water? It increases. Explain at particle level how this system will reach thermal equilibrium. Water's particles hit, whoa, that's different, iron and transfer energy. H2O loses energy and iron gains energy. After systems reach thermal equilibrium, how does the average kinetic energy of the iron compare to the average kinetic energy of the water? They are equal. Remember, average kinetic energy is essentially temperatures are equal. Describe each variable in the equation below, including units. Q is heat. I'm just going to give one unit. Joules. M is mass, which is grams. Watch out, it could be moles. C is specific heat. And that's in joules per gram degree Celsius. And delta T is change in temperature in degrees Celsius or kelvins. What is the first law? Oops, let's put that back up there. What is the first law of thermodynamics? First law of thermodynamics is energy is not created nor destroyed. It just changes forms. Reaction is carried on a styrofoam calorimeter. The reaction is known to release 15.2 kilojoules of energy. However, when the reaction is carefully measured, all calculations performed, the reaction give off only 15 kilojoules of energy. Explain why it is not possible to lose that. And there's the first law of thermodynamics. B, if not to the surroundings, where could that energy have gone? Could it have gone to the thermometer? Some of the water may have evaporated, boiled away, and took away some energy. Collision theory, nonsense, incomplete. Now, I shouldn't leave the word nonsense on there, but that's it. We talked about that one in class. I typed it. Of incomplete reaction gives a lesser result. Two different metals of equal mass at the same initial temperature are given the same amount of energy. Explain why the two metals would not have the same temperature. Okay, so that temperature is solved by Q equals mc, and I'm going to do T sub F minus T sub I. Okay, so they both have the same, here's what's the same. They have the same initial energy. They have the same mass. We're doing the same Q, but what's not different is, what's not the same is C. Because if they're different metals, they have a different C. And that means you're going to have a different T sub F. Hey, my favorite way to describe something, algebraically. Okay. So the yellow things are the same. The two things that change are C. So if C goes up, T sub F goes down, etc., etc., etc. Would the metal with a higher specific heat capacity have a higher temperature, lower temperature, or the same temperature? Two different metals of equal mass are given the same amount of energy, so the temperature is going up. So a bigger C means smaller delta T. So the metal with a higher specific heat, so bigger C, would have a lower final temperature. For both metals. Well, increasing the C gives you smaller, so I guess if I have to do a calculation of both, smaller C gives a larger delta T. Q equals mc delta T algebraically. Closed system of a piece of ice. A closed system means that we're assuming no heat is lost to the surroundings, and metal is created. The 5-gram piece of ice at minus 5 degrees Celsius melts to a liquid at 10 when placed on the metal. The metal has an initial temperature of 75. Why did the ice melt? It absorbed energy from hot metal. Let me read that again. A 5-gram piece of ice at -5 melts to liquid water at 10 degrees Celsius when placed on the metal. The metal has an initial temperature of 75. So I'm going to assume that final temperature is 10. Is the energy of the entire system after the ice melts less than, greater than, or equal to system before? It's equal. First law of thermodynamics, which is energy is neither created nor destroyed. They said it's a closed system, so it's not being lost. Which has more energy, the ice or the liquid water? So again, remember how I like to do the liquid solid? So the liquid water has more energy. What happened to the overall energy of the metal? The overall energy of the metal went down. Why? Gave to H2O. What happened to the overall energy of H2O? It went up. Solid to liquid, absorbs from the metal. Explain your answer to D and E in terms of the first law of thermodynamics. Well, energy total is constant. So the energy that went down for the metal equals the energy that went up for the water. All right. Convert the following either specific heat capacity or molar heat capacity. So we did this right here. Notice right here we've got joules per gram degree Celsius, canceling grams. That's it. Hi, Michelle. And we get this answer. Convert to specific heat capacity, 24.3 joules per mole degree Celsius. 24.3 joules per mole degree Celsius. Make sure it's water. Oh, well, for aluminum. Okay. So again, I want to get rid of the moles. Put the wrong thing there. 1 mole of aluminum is 26.98 grams of aluminum. .901 mole. Nope, moles are gone. Still have joules per gram degree Celsius. Convert molar heat capacity. So we got gold. Give me one I don't know the mass of. So 0.129 joules per gram degree Celsius times grams of gold. 1 mole of gold. It was 196.97. I knew that. Multiply that out. 0.129 times 196.97. Again, notice how grams go away, moles are added. And I get 25.4 joules per gram degree Celsius, except for I put gram and I meant to put moles. Same thing here, joules per mole degree Celsius. Getting rid of moles. I have grams there, and that gives me my joules per gram degree Celsius. A 200 gram metallic cube is placed in a coffee cup calorimeter with 100 grams of water at 20 degrees Celsius. The metal releases 7.2 kilojoules of energy in the water. What is the final temperature of the water? So the first thing I'm going to do is change 7.2 kilojoules to 7,200 joules. So a 200 gram metallic cube is placed into a coffee cup calorimeter with 100 grams of water at 20. The metal releases that much heat, so the Q of the metal equals 7,200 joules. What is the final temperature of the water? So the water is going to absorb all of that. So I'm going to do for the water, this is for H2O, I'll label it thus. Q equals MC delta T. So my Q is 7,200 joules. The mass of my water, where'd it go? 100. Specific heat of the water is 4.18. Final temperature is T sub F minus T sub I, which is 20. Let's do some math. 7,200 divided by 100 divided by 4.18 means 17.22 equals T sub F minus 20. T sub F equals, I can do that in my head, 37.2 degrees Celsius. So it went up, big surprise. All right. Determine the amount of heat needed to melt 125 grams of gold, originally at 298 K. So the melting point of gold is 1,094. So that means I'm going to start with, so this is going to be 1064 is the melting point. We're going to assume it's a solid. So we start at 298. So I got to go up here, and then I got to melt it. So Q is going to be MC delta T. That's this part, plus M delta H fuzz. That's that part. Mass of the gold is going to be 125 in both cases. The specific heat of gold, I'm going to add, that has to be a solid there, 0.128. Change in temperature is 1064 minus 298. I honestly would put that in my calculator and drop it in, but just so you know where it's coming from. Still 125. And then, oh, you didn't, you dirty dog. Notice how this is kilojoules per mole. So that means it's 1255.0 joules per mole degrees Celsius. And I got to change that to grams. So 1 mole of AU give back my gold, and grams of AU give back my gold. And we just did, this is 196.97. Come on, memory, 97. So see how those units are just dirty dogs here. Divided by 196.97, 63.7 joules per gram degree Celsius. So this is going to be 63.7. 125 times 0.128 times quantity 1064 minus 298 close quantity equals plus quantity 125 times 63.7, and that is 2218 joules, which would be 20,200 joules or 20.2 kilojoules. All right, so what temperature change is shown for the reaction below? So this is reading thermometer that we typically do badly. This is 25, 21, 22. This is 22.5. This is 25, 26, 27, 28. I'll call that 28.0. So I went from 22.5 to 28.0, and that is 5.5. Let's subtract that. All right, and you do have to go to the tenths place. Tenths. All right, the hydrocarbon pentane is combusted to produce carbon dioxide and water, shown in the unbalanced reaction below. Complete combustion of 5 grams of pentane releases 243 kilojoules of heat. On the basis of information, calculate the value of delta H for the complete combustion of 1 mole of pentane. So 5 grams, I'm going to turn that into moles. So grams and moles, 1 mole, C5H12. Go on the periodic table and add that up. 12.01 times 5 plus 12.12 for my hydrogens, 72.17. 5 divided by that answer is 0.0692 moles of C5H12. So I just set up a proportion from this. So if 0.0692 moles equals 243 kilojoules equals X moles over, oh, not X moles, it's going to be 1 mole, my bad, 1 mole over X kilojoules. So cross multiply, and I have 243 divided by 0.0692, and I get 1 mole, or X, equals 3511 kilojoules. So 3,511 kilojoules. Determine delta H in kilojoules per moles of reaction. This per moles of reaction means balance it. Oh. So let's see here. 5 carbons, 12 hydrogens, 12 hydrogens. I've got 6 oxygens plus 10 oxygens is 16. There's 8. Kilojoules, it's the same. It's the same because 1 is the coefficient. If the coefficient was 2, then I would double it, or blah, 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 blah. Use the heating curve of pure ethanol given below to answer questions 29 through 33 below. What is the melting point of ethanol? That's the lowest point here. That is 150 degrees. Oh, sorry, not degrees, 150 Kelvin. Boy, that doesn't sound right at all. And the boiling point is 350 Kelvin. And that is, on that, remember the first plateau is the melting point. It's a lower energy one, and the second plateau is the boiling point. Explain why Q is shorter than S, referring to specific intermolecular forces of ethanol. Okay, so that means it's an ethanol, so we're going to talk about H bonding. For solid to solid is stronger because using Coulomb's law, bond energy equals Q1, Q2 over radius squared. Particles are closer as a solid than as a liquid, and R squared increases in a liquid because the particles are farther apart. Distance increases. All right, which line segment represents the enthalpy of fusion? Enthalpy of fusion is melting. So the line segment and enthalpy of vaporization is boiling. So since I'm moving back and forth. So the line segment that represents melting would be the one on the melting point, Q, and boiling would be S. So Q, S. Explains what's happening on a molecular level at PRT. So at PRT, kinetic energy increases, temperature increases, and velocity of particles increase. Is the specific heat capacity of gaseous ethanol greater than, less than, or equal to specific heat capacity of liquid ethanol? Okay, so remember, gentler slope equals larger C. So let's take a look. Gaseous ethanol. Oh man, I got to count this out. One, I'm looking for where it actually hits real buttons here. So it's rise over run. 1, 2, 3, 4. 4 over 1, 2, 3 is what a gas is. And then, liquid. This one is 1. So 1 over 1 is liquid. So 4/3 is 1.33. This is 1. So a liquid. The liquid has a gentler slope. So it has a larger, let's see, 3 moles of a gas undergo a phase change below. How much energy is absorbed or released? So all we're doing is a phase change. So Q equals mole, notice moles, delta HVAC. So 3 times 25 is 75 kilojoules. And it's released because you go from a gas to a liquid, and it goes down. Use the heating curve of methane. Answer the questions 35 through 40 below. How much energy does it take to melt a mole of methane? Melting is this right here. So 0.94 kilojoules per mole. So how much energy does it take? 1 mole. Get rid of the per mole. 0.94 kilojoules. It is endo because, again, if you're melting it, you're going from a solid to a liquid. So see how that's going up in energy? So it has to absorb energy. All right. How much energy does it take to vaporize 1 mole of methane? 8.2 kilojoules. Is this exothermic or endothermic? So vaporizing is going from a liquid to a gas. So you're going up, it's endo. How much energy does it take to freeze 1 mole of methane? Notice they're going to be the same. 0.94 kilojoules because you're just changing directions. This would be exo. You're going the opposite direction. Condense, again, same as boil, 8.2 kilojoules. Exo because you're going from high to low. How much energy does it take to freeze 9 grams of methane? Okay, so for this one, I have 9 grams of methane, which is CH4. I'm going to change it into moles because that's my delta H fusion. So this is 16.04 grams, periodic table. 1 mole CH4. 9 divided by 16.04. It's 0.561. And then freezing is Q equals M delta H fuzz, which is 0.561 times 0.94. Q equals my 0.561, 0.594, 0.527. What unit am I in? Kilojoules. Now notice it's kilojoules because that's where that came from. Okay. How much energy is released when 45 grams of methane condenses? So that's the same, different mass. 45 grams, CH4, 1 mole, 16.04. 5 or 16.04, 2.81 moles. Q equals M delta H VAP. It's vaporization because you're unboiling it. So we're actually using moles here, I guess. So 2.81, and I use moles because that is what they gave this to me per mole. That's why I'm using kilojoules for what it comes out at. So 2.81 times 8.2. And that's going to be times 8.2, 23 kilojoules. And that's it. So hope you enjoyed that part. Toodles.